Hello everyone, and welcome back to this Nanophotonics and Plasmonics course. With this video, we're going to discuss more extensively about localized phase plasmon resonance and how we can calculate them using analytical methods. The quasi-static approximation we've discussed in the previous video is only valid for nanoparticles that are very small, so roughly speaking below 100 nanometers in size. So of course, there's no clear limit, and it is going to depend on the composition of the nanoparticle as well as the surrounding environment. For larger nanoparticles, where the phase change of the incident electromagnetic field will basically be significant over the nanoparticle volume, then you're going to need more rigorous electrodynamic approach to calculate the electric field and magnetic field component that will result from the interaction of an incoming plane wave with a nanoparticle. So, solutions of Max's equations in the case of spherical particles is described by the Mie theory, which was developed in 1908 by Gustav Mie. A few years later, there's been some extension that has been done for ellipsoidal nanoparticles, which is known as Gans theory or Mie Gans theory. However, it's important to notice that the Gans theory is just an expansion of Mie theory, but it also requires a certain level of adoption of the quasi-static approximation. So this Mie theory is an analytical method and solves a certain number of limited cases of the scattering problem in general. So this is a method which is solving the scattering problem we discussed in the previous video. But this is only limited to spherical geometry. So the particles need to be spherical. They need to be composed of matter which is homogeneous and isotropic. And this can be actually calculated only for the case of an incoming plane waves. There's been, of course, some extensions that have been generated over the years for concentric spheres. So basically, this is multi-layered spherical geometries, including core shell spherical particles. There's also an extension for an ensemble of spheres. This is known as generalized Mie theory. And as we just discussed, also some extension for ellipsoidal, like the Mie Gans theory. So what this theory is about, so we're going to just discuss a little bit the math behind. So don't be scared. There's a lot of math. You don't have to memorize that. This is more to illustrate what's behind the scene when you do a simple Mie calculation. So because of the spherical geometry of the system, the problem is fairly simple, so to speak. So it's really reduced to this simple equation here. So this is just the Laplace's equation. So this Laplace equation where this term is just the Laplacian in spherical coordinates. So keep in mind we have spherical geometry, so it's more convenient to deal with spherical coordinates rather than Cartesian coordinates. So we can obtain solutions of this equation, of this Laplace equation. So the solutions are basically just taken from linear combinations of odd and even solutions. That is basically what you get for those solutions of this particular equation. You have the Legendre polynomials in this equation. You have Bessel's functions. So these are functions that you may have seen or that you will see in mathematical physics too. So what do we do with this? When we have this type of solutions, then we can actually calculate the electric field and the magnetic field. And for that, we need to introduce additional mathematical objects, which are here known as vector harmonics, M sub Lm and N sub Lm. So these are basically just extensions of the traditional spherical harmonics, but used for use with vectors. And they are calculated directly from the solutions we obtain from Laplace's equation. So once you have the solution from Laplace's equation, you can calculate those vector harmonics. Once you have those vector harmonics, you can calculate the electric and magnetic fields, where those indices now, U and V, are the solutions of scalar equations. So don't worry if you don't understand necessarily everything. That's not the point. This is just to show you the different steps, and I will summarize everything at the end of these slides. So those solutions, U and V, basically are just calculated outside and inside the particle. So for both regions of the scattering problem that we discussed before. So outside of the particle, we are really looking at the scattered waves. So we can calculate the solutions of the wave equations outside of the particle. So you see that those very complex expressions. You can see that you have this integer L, which is going to be referring to the order of the Plasmon resonance that we discussed already, and we're going to discuss a little bit more in details in a moment. You still have these Legendre polynomials that show up in all those solutions. You have a mixture of spherical Henkel functions and spherical Bessel functions when you calculate those solutions U and V inside and outside the particle. It has to be noticed that you have those coefficients here. You have these coefficients A, B, C, and D. Those coefficients are known as the Mie coefficients. These are the most important things you're going to be calculating using theory, or those coefficients A, B, C, and D. And they can be derived from a very long series of mathematical derivations, long algebra. I spare you the math here and just show you those coefficients. So you don't have to memorize them, obviously. It's just to show you what they look like. So you have, of course, the Mie scattering coefficient, which basically are the coefficients outside the sphere, A and B. We're going to come back to them in a minute. And you have the Mie coefficients for the fields inside the sphere. So you see that they depend on this psi function and this xi function. Those are basically just Riccati-Bessel functions, which are just a slight modification of the Bessel and Henkel spherical functions. So Bessel functions, Henkel functions, Legendre polynomials, these are the mathematical objects that are used in Mie theory along with vector harmonics. So why do we show all of these? Well, simply speaking, the idea, once again, is to calculate those coefficients, A, B, and C, D. Once you have those coefficients, A, B, and C, D, then you can basically use those coefficients to calculate the solutions of the wave equation, U and V, that we had on the previous slide. Once you have the U and V inside and outside of the particle, you can use those guys to calculate the vector harmonics, M and N. And then from those vector harmonics, you can calculate the electric and magnetic fields, which are the physical quantities we are interested in. Those coefficients, especially the A and B, are also very important because they allow you to actually calculate the optical cross-sections that are the properties that we can actually measure experimentally. If you measure a spectrum, an absorption spectrum, a scattering spectrum, and that's basically going to tell you where the Plasmon resonance is. So once you have those Mie scattering coefficients, you can calculate the scattering cross-section. This is the expression for the scattering cross-section as a function of those Mie scattering coefficients A and B that you would have calculated through the previous expressions in the slide before. You can calculate also the extension cross-section. So you see that now you're taking the real part of this sum of coefficients, and by taking the difference between the extension cross-section and the scattering cross-section, then you can obtain the absorption cross-section. So these are the spectra that we're gonna see in a second. That basically gonna allow you to characterize the optical properties of your nanoparticle. Something which is very important to notice, though, is that the Mie theory is really basically solving the scattering problems. This is why we can actually calculate directly the scattering cross-section and extension cross-section from the Mie coefficients. And the absorption cross-section is calculated indirectly from the extension and the scattering. Well, once you calculate those cross-sections, what you're going to get is basically a spectrum. So these are three examples for gold nanoparticles, silver nanoparticle, and aluminum nanoparticles of same size, 150 nanometers, immersed in water. And you have the blue, which is the extension spectrum. That's the expression in the middle here. The red one is the scattering spectrum. That's basically the first expression up there. And then at the bottom you have the green, which is the absorption spectrum. So you can see that for the same size and same surrounding environment, because you change the composition, you're going to change the response. So no more just a single Lorentzian resonance as we obtained with the quasi-static approximation. Now we observe additional features that are showing up and that we're going to discuss in a moment. Three things we can see already, and we're going to come back to that also. First, you see that the resonances are much broader than we saw before. Second, we have additional peaks that are basically higher order Plasmon modes. So we have no more just the dipole, but we have also quadrupoles, hexapoles, and so on and so forth. Because we are basically looking at a summation over those different terms. So now we have these summations that show up in optical cross sections, and that's basically summing every term from L equal 1, which is a dipole, L equal 2, a quadrupole, L equal 3, an hexapole, all the way to infinity. And the final thing we see is that those resonances are actually shifted, and we're going to see that also in a minute. So they're shifted spectrally toward longer wavelength or lower frequencies. So the quasi-static approximation breaks down in two regimes. We just saw the first one. So when you have large nanoparticles beyond 100 nanometers in size roughly, then we have to include retardation effects. And this is because light travels with a finite speed, and therefore it takes time for light to go from one side of the nanoparticle to the other side. So this includes some phase change throughout the nanoparticle. If you have a small nanoparticle, if you have an incoming plane wave, because of the size of the nanoparticle is much smaller than the wavelength of this wave, then the particle basically sees a field which is fairly uniform. So you see that you have a field, electric field, which is fairly uniform across the size of the nanoparticle. And that's basically going to generate only a dipole moment. And this is basically what justifies the quasi-static approximation. Now, when you have a larger nanoparticle, because the size of the nanoparticle then is comparable to the wavelength of light, then on one side of the nanoparticle, you may have actually a different type of electric field than the other side. And this phase change is going to be responsible for inducing different type of charge distributions on both sides. In this particular case, we are illustrating a quadrupole resonance. So you have now positive charge, negative charge on that side, and the other side is going to be negative and positive. So you see that you're forming a quadrupolar pattern. So that's why we are able to actually excite higher order modes in large nanoparticles. This is because of retardation effect. And therefore, in that particular regime, the quasi-static approximation fails. This also leads to spectral redshift of the Plasmon resonance. We just saw that, and we're going to see that on the next slide. You're going to see the Plasmon resonance shifting spectrally. And as well, we're also introducing some higher order modes, as I've just mentioned. There's also some significant increase in radiation damping, because as you increase the size of the nanoparticle, the scattering will increase. And because you scatter more light, the nanoparticle will actually lose more energy more rapidly, and therefore the plasmon will die out more quickly. So because it dies more quickly in the time domain, it's going to be a very short-living plasmon. When you Fourier transform and you go to the frequency domain, then you're going to obtain some resonance going to be very broad. So you're adding damping, you're adding broadening of the resonance as you increase the size, because you increase the total amount of scattering and energy loss on the particle. When you have very small sizes, typically below 10 nanometers, then you have basically more surface scattering. So we talk about surface scattering here. This is the electron scattering from the metal at the surface of the nanoparticle. So this is not light scattering. This is basically just the electrons that are basically oscillating in the plasmon oscillation. Those conduction electrons that are oscillating, as they oscillate, they can actually scatter at the surface of the nanoparticle. So when you scatter at the surface of the nanoparticle, basically the plasmon coherence, the collective oscillation is basically dying out. You're losing the coherence as you're losing electrons in this process, and therefore the plasmon will die out, and you're gonna basically end up adding some additional broadening to the resonance. So this is happening when the nanoparticle size is roughly of the order of the electron mean free path in the metal. So you're decreasing the plasmon lifetime, or you're increasing the spectral broadening, so you have broader resonances. And you can account that basically by adding these additional damping terms. So the total broadening or damping that you observe for a given plasmon resonance is going to be function of the size. So this is the natural broadening of the resonance. So this is like if you have an ideal case and no surface scattering, and this term here accounts for the surface scattering. So you see that now you have additional broadening, which is inversely proportional to the size of the nanoparticle. So the smaller the nanoparticle, the larger this surface scattering damping. So if you calculate the spectra, the optical cross sections using Mie Theory for a silver sphere, and you change the size continuously from 10 nanometer all the way to 300 nanometers, this is what you get. So you have a single Plasmon resonance, which is a sharp Plasmon resonance. You see that you have a transition in terms of ratio between scattering and absorption, and then you have these additional peaks that are showing up. In addition to the localized phase Plasmon dipole resonance, you have this broadening of the resonance that show up, and you see that this Plasmon resonance are shifting toward higher wavelengths. So this is when you increase the size continuously from 10 nanometer to 300 nanometers for a single sphere, and then you end up with a spectrum that shows a lot of different resonances. So if we just break down this sequence a little bit, this is what we got. So if we have a very small nanoparticle, you have only one very narrow Plasmon resonance. That is what we have in the quasi-static approximation. So you see that in that particular case, most of the extension is actually absorption. So you have a strongly absorbing nanoparticle, very little to no scattering. As you increase the size a little bit to 50 nanometers, you see that now you have more scattering. So you have a fairly equal contribution of scattering and absorption to the extinction cross-section. You start seeing some slight broadening of the Plasmon resonance. As you further increase the size to 100 nanometers, now you're in this range where quasi-static approximation fails. So you see that you have a significant broadening of the dipole Plasmon resonance. You see that you have a shift. Now you're close to 400 nanometers as opposed to 350 that you had before. You start seeing this additional peak that shows up. So this is now the L=2 or quadrupolar mode, and then it's basically showing up in the shoulder as a shoulder of the dipole or L=1 Plasmon mode. If you further increase the size, you have more broadening. So you see that the dipole is basically dying out because of so much broadening. So there's so much radiation damping that basically this mode is very short-lived. You see that the quadrupole is increasing in intensity, and then when you increase to very large sizes, you have those additional modes. So now you have the dipole, the quadrupole, and other modes like hexapoles. To summarize, we have a spectral shift. It's a red shift. You have an increase in radiative damping of the Plasmon resonance. That's leading to larger, broader resonances, and you have also excitation of higher order modes that are basically like quadrupoles, octopoles, and beyond. So this is what you can get beyond the quasi-static approximation. So using Mie Theory. So what are those multipoles that we talk about? So if you just take the case of an aluminum sphere, 150 nanometers in size, placed in water, you send an optical excitation, a plane wave, which is polarized along the vertical axis, propagating from left to right on this schematic. Then therefore you obtain those spectra. So you have the extension, scattering, and absorption spectra, and you see you have 1, 2, 3, 4 resonances in this particular spectral range from 200 nanometers all the way to 1000 nanometers. So what do we get? So if you look at what's this resonance, so basically when you excite the nanoparticle at this particular resonance, then you generate a local electric field around the nanoparticle that distributes this way. So this is the aluminum nanoparticle when excited at this Plasmon resonance, which is about 580 nanometers wavelength. And you see that you have a very strong local electric field intensity on both ends of the nanoparticle. So they are aligned with the incident electric field. So this is the dipole resonance, or L=1. Now if you excite the nanoparticle at this particular resonance here, 320 nanometers, then this is what you obtain. So you can look at the distribution of local electric field around the nanoparticle. It's very enhanced in those 4 lobes. So you have a 4 lobe pattern. So this is a quadrupolar resonance, or L equal 2. Then you can look at the other 2 resonances. You have the hexapole with 6 lobes, and octopole L equal 4 with 8 lobes. So a couple of things to notice here. So you see that there's actually it's not symmetric left-right. So you see that those lobes on the right hand side are more pronounced than the lobes on the left hand side, and this is the same for all of them. You see that the dipole is not perfectly at the top or at the bottom; it's slightly offset to the right, and this is because of retardation effects. So as light propagates from left to right on this schematic, it takes time for light to propagate from one end to another, and by the time the optical wave arrives on the right hand side, the left hand side is already starting to decay and is less pronounced. So that's why you have this symmetry breaking left right. So this is basically what a schematic representation of the dipole resonance will look like. So this electric field distribution up and down is basically the result of this displacement of electrons with respect to the ion background. It's basically just going up and down following the electric field oscillation, and you generate this induced dipole moment represented by this black arrow. Now if you're looking at the I-order mode, like a quadrupolar mode, this is basically what it could look like. So if you have now this 4 lobe pattern, this is because you have this oscillation of the electron gas. So you have this squishing on one direction and extension on the other side. So you have this in phase and out of phase type of excitation that basically generates this quadrupolar plasmon resonance. Now, something which is interesting to notice, you see that you don't see any black arrow, is because of the distribution, positive, negative, negative, positive on the other side. It's basically resulting in a 0 net dipole moment. So this quadrupole does not have a net dipole moment. So what's beyond Mie theory? So we know that Mie theory is only limited to very simple cases. So we can wonder, what about other geometries? Can we calculate the plasmon resonances, optical spectra, near field distributions for more complex geometries? The answer is yes. And we need electrodynamic numerical simulations to do so in order to solve Max's equations for more complex geometries. So I encourage you to go back to chapter 7, and basically these are just some of the methods you can find that basically solve Max's equations for any type of arbitrary geometry. So finite difference time domain, finite element method, discrete dipole approximation, boundary element methods, and you name them. I'm going to actually publish another short video that will actually walk you through FDDD simulation of Mie scattering for spherical geometry, so you can calculate the electric field distributions that we've seen, as well as the optical cross sections. So those numerical methods, they are very powerful because they are full wave methods to solve the full set of Max's equations without any assumption or approximation. So they're also fully retarded, meaning that they include those retardation effects that really account for the radiation damping, the phase change of the field as it moves across the system. And finally, they can really endure any type of geometry. They can really look at particles that are isolated or coupled in periodic arrays or on substrates, multiple composition, very complex geometries. You can even import and include geometries that are directly deduced from experimental images like TEM or SEM images. So this is very powerful, and this is what is needed to go beyond Mie theory.